In this section, I want to consider objects on inclined planes and how friction plays into that. And these are a little more advanced topics than we have dealt with before. In this case, we have a box, and it has a center of gravity, as you can see in the picture. It weighs 500 pounds. There's a 35-degree angle of the inclined plane, and there's a coefficient of friction of 0.5, and we want to find out how much force is required to keep it from tipping or slipping downhill. So we have a two-scenario situation that we have to consider. So let's draw a Freebody diagram, and got a center of gravity. There's going to be an mg sine theta, mg cosine theta. There's a pushing force. I'll put that P here. Let's consider the slip scenario first. So in this case, we don't have to have a point of rotation, and there's going to be a force of friction. If it's tending to move downhill, then the force of friction would be going uphill. All right, so we're going to assume slip and see what we get. If that's the case, then force of friction is equal to mu normal in that situation. So let's sum the forces in the y is equal to 0 and see what we get. Minus mg cos theta plus normal is equal to 0. So here normal is equal to mg cosine theta. And if we sum the forces in the x is equal to 0, so I'm going to have uphill as my x, positive x. This would be positive y in that direction. So I have plus p minus mg sine theta plus the force of friction, and force of friction here is equal to mu normal, and that is going to be equal to mu, and the normal is mg cos theta equals 0. So let's put some numbers in and see what we get. P says that the box weighs 500 pounds, sine of 35 degrees, mu is 0.5, again 500 pounds, cos 35 is equal to 0, so P to keep it from slipping is equal to 82.0 pounds. Okay, so that is the slip scenario. Let's consider the tipping scenario. I can move that up a little bit, I believe. Let's consider the tip scenario. I'm going to draw another Freebody diagram, but in this case, the normal force moves to the point of rotation. In other words, if the tip, it's going to move this way. This is going to be the tipping point, the tipped rotation, and A goes to 0. So tip, let me just write my little note to myself. At tip, it will rotate, and let's call this point B, rotate at B, and A goes to 0. All right, let's go ahead and put our forces back in here. Mg sine and mg cos. Still got a pushing force right there. And the force of friction goes this way. All right, but when we're analyzing tipping, all we have to do is do a moment equation about the point of rotation, which is B. So sum of the moments about B is equal to 0. And so I have minus P times, and that has a lever arm of 4.5. That's right there, this lever arm right there. Plus mg sine theta, and its lever arm is 3.5. And you can see that right there, 3.5. And it's positive because it's going in this direction. That's our positive rotation direction. Then mg cosine theta is actually going in the negative direction. Mg cosine theta, and it's got a lever arm of 1.5. That's right there, 1.5. And that's equal to 0. All right, let's plug the numbers in and see what we get. Minus P times 4.5 plus 500 sine of 35 degrees times 3.5 minus 500 cos 35 degrees times 1.5 is equal to 0. Solve that for P, and I got that is equal to 86.5 pounds. So in this case, they're pretty close. Not much difference between the tip scenario and the slip scenario. But basically, the lower the force, the force that the scenario that requires the smallest force is what will happen first. So in this case, this is the smallest force required to keep it from tipping or slipping. All right, in pulley situations, this is a pulley situation which is a little more complicated. And here you need to assume a direction and then validate your assumption with the answer that will kind of happen. So in this case, A weighs 40 pounds and B weighs 80 pounds. Which way is it going to move? You can see the pulley deal here, the pulley situation. We know that there's pulleys just transfer forces, and so in this case, this is a ideal frictionless pulley, not a torque belt situation or not a belt friction situation. In that case, we have tension is going to be the same tension on all three of those pulleys. Let's assume that B slides downhill. So I'm going to call this my positive direction. If that's the positive direction for B, then this will be the positive direction for A. In other words, B will slide down and it will pull A uphill. All right, in order to validate that, let's do some free body diagrams. So let's do free body diagram of number A. It has two tensions pulling it up. It's got an mg sine theta and mg cosine theta. Now I can go ahead and put the degrees in here. I think that would probably be fine. This is going to be cosine of 60 degrees, and this is sine of 60 degrees. It's got a normal force. Now, if it is positive going uphill, that means the force of friction is going to be opposing that motion. I know if it's a slip scenario, force of friction is equal to mu normal. And because there aren't any other forces in the y direction, I can just by observation say that the force of friction is equal to mu mg cos 60. Okay, let's sum the forces in the x direction. This will be the positive x direction going up. Sum of the forces in the x is equal to 0. So in this case, I have minus mg sine 60 plus 2t minus mu mg cos 60 equals 0. All right, let's put the numbers in and see what to get. Minus 40 sine of 60 plus 2t minus mu. Mu is my unknown here, so I'm just going to keep that as a variable, times 40 cos 60 is equal to 0. And I can solve this for t is equal to 17.32 plus 10 mu, or mu times 10. Okay, obviously I can't solve that for mu quite yet. What we're looking for is the value of mu for this situation to stay in equilibrium. All right, let's move over to part B. So I'm going to draw a free body diagram of B. Again, this guy is going mg sine theta. In this case, it is sine 30 degrees. Mg cosine of 30 degrees. This has a different weight. It's got mg of 80. It's got a normal force here. There's a tension pulling it up the hill. Let's see if I can make a little better tension. Now, which way is the force of friction going to go here? I've declared that positive is going down the hill. And if it moves down the hill, that means the force of friction is going up the hill like this. And again, this is a slipping scenario. We're trying to solve for the for the mu to keep it from slipping, so I know the force of friction is equal to mu mg cos theta. All right, let's sum the forces in the x and see what we can find. Sum of the forces in the x is equal to 0. So positive is down the hill, so I'll say mg sine of 30 minus tension minus the force of friction is mu mg cos 30 is equal to 0. Let's go ahead and put all these things in here. We have 80 sine of 30 plus minus the tension, which would be 17.32 plus 10 mu minus mu times 80 again, 80 cos 30 is equal to 0. And do a little algebra and you can solve that for mu is equal to 0.286. And that's how we set that up. That is the minimum mu to prevent slip. And that's kind of a concept, is how much friction do I need to keep it from slipping? That's the same thing as what is the value of mu for equilibrium. This is the minimum mu to prevent slip. If I had a greater mu, that would mean it would obviously not slip anymore. If mu was less in this situation, then it would be in a slipping scenario. It'd be a dynamics problem. Things would be accelerating. Now, how do I know that this is a good answer? I assumed that positive was down the hill for this guy and up the hill for this guy. I made that assumption, did my all of my equations with that assumption. In other words, force of friction pointing up the hill, in this case, force of friction going down the hill, based on what I did. I got an answer that makes sense. In other words, I got an answer that's positive based on all of my work here. So by that, I can conclude that I made the correct assumption, that it is actually going up for this one and down for this one, and that is a good answer.